Hello, hello. Okay, so our next speaker is Tom Rudelius from Berkeley, and he'll talk about consequences of no global symmetries in quantum gravity.
Great, thanks, Sakura. And let me also say thank you very much to the organizers for the invitation and for putting together this nice conference. So my talk today is going to be based on a series of papers with a number of different collaborators whose names you can see here. And before I get into all of the gory details, let me talk about, sorry, I'm hearing my little echo here. I don't know if that's, maybe it's just me. So before I get into all the gory details, let me start out by talking about how this fits into the bigger picture. So in recent years, there's been a bit of a revolution in quantum field theory, driven by the discovery and the development of generalized notions of global symmetries. Examples include higher form global symmetries, in which the charged operators are higher dimensional objects, non-invertible symmetries, which involve not a group, but rather a more complicated category, and higher group symmetries, in which two or more higher form symmetries are, in a sense, mixed up into a larger structure. Meanwhile, recent years have also seen a rejuvenation of interest in identifying universal features of theories of quantum gravity. This is a very active area of research, and the overall picture is still coming into focus. But there are a few specific areas within this larger field where the picture has become relatively clear. These include the absence of global symmetries in quantum gravity, the completeness hypothesis, which demands the existence of states in every representation of the gauge group, and the weak gravity conjecture, which demands the existence of a particle whose charge-to-mass ratio is greater than or equal to 1 in Planck units. The main point of my talk today is to argue that these two areas are closely related. Much of our understanding of quantum gravity can be viewed as a consequence of the absence of global symmetries, which means that generalized global symmetries hold power not only for quantum field theory, but for quantum gravity as well. So with this, let me give a lightning review of the history of the absence of global symmetries in quantum gravity. Back in the 70s, Hawking noted that an evaporating black hole emits particles without regards to their global charge. This means that black hole evaporation violates global symmetries and destroys global charge. Since this time, many different physicists from various different lines of reasoning have reached the same conclusion, that quantum gravity does not have any exact global symmetries. This strongly suggests that any would-be global symmetry, which may exist in a quantum field theory, must be either gauged or broken upon coupling the theory to gravity. And several of these lines of reasoning likely apply to generalized notions of global symmetries as well. So this brings us to our first generalized notion of a global symmetry, which is what's known as a higher form global symmetry. A Q-form symmetry is a symmetry for which the charged operators are Q-dimensional. So the case of an ordinary symmetry that we learn about in quantum field theory classes would correspond to Q equals 0. The charged operators are local operators. For a higher form symmetry, though, the charged operators are line operators, surface operators, etc. Global symmetry transformations form a group G, which may be either discrete or continuous. In the ordinary case, it may be non-abelian, but for a higher form symmetry, it's necessarily abelian. If G is continuous, then in most cases, there will be a conserved D minus Q minus 1 form another current, which is closed. In the modern view, symmetries in quantum field theory are implemented by operators known as symmetry generators. These operators are D minus Q minus 1 dimensional for a Q-form symmetry. They're labeled by elements of the group, and they fuse according to the group multiplication law, G times G prime equals G double prime. These operators are topological, and as we'll see, this is really the hallmark of a generalized global symmetry, the existence of topological operators. By topological, I mean that this operator can be deformed, and as long as this deformation process is nice and smooth and we don't cross over any charged operators in the process, then any correlation function involving this operator is going to be equal to one involving this operator. In the case of a U1 symmetry, where we have another current, we can be a bit more explicit about the form of these operators. Namely, they're given by the exponentiated integral of the another current over this manifold M, where here alpha labels the element of the group. Symmetries in quantum field theory are associated with word identities. In the language of these charged operators, the word identity says that if we take a charged operator, surround it with a symmetry generator, then this will be equal to the charged operator we started with times a representation of the group, or in the abelian case, simply a phase, which depends on the element of the group G and the charge of the operator V. Pictorially, what's happening here is that we're surrounding this charged operator with the symmetry generator, and because this operator is topological, we can change its size and its shape at will until we can shrink it as much as we like, and the word identity says that if we shrink it all the way to a point, we simply pick up a phase. The prototypical example of a higher form symmetry comes in just ordinary pure Maxwell gauge theory. So this is an ordinary zero form symmetry, but it has a one form electric global symmetry. The another current of the symmetry is up to normalization, just star F. Its conservation follows from Maxwell's equations, d star F equals 0, in the absence of charged matter. And it's a one-form symmetry, so the charged operators are line operators. Namely, they're just the Wilson lines of the theory. And this is why we refer to it as an electric symmetry as opposed to, say, a magnetic symmetry under which 't Hooft operators are charged. The word identity for this electric one-form symmetry tells us that if we compute the exponentiated integral of the electric flux through a two-sphere, which links with this Wilson line, then this is just going to give us some, this is just going to ultimately compute the charge of the Wilson line. And note here that the charge computed does not depend on the size or the shape of this operator. This is a manifestation of the fact that the operator is topological. It's also a manifestation of the more familiar Gauss's law. Recall, Gauss's law tells us that the flux through a closed surface is equal to the charge enclosed, irrespective of the size or the shape of that surface. This symmetry will be broken in the presence of charged matter. This is easiest to see from the modification of the another current. So d star F is no longer equal to 0, indicating that this symmetry has been broken in the presence of the charge N matter. Another way to see this is from the fact that the charge N Wilson line can end on a local excitation of this field. And this is important because it allows us to unlink this topological operator and compute this setup here in two different ways. So first of all, we could use the word identity to shrink this operator to a point, and we pick up this phase. Alternatively, we could unlink it from the Wilson line and then shrink it. Equating the left and the right-hand sides, we learn here that e to the I alpha must be an nth root of unity. In other words, in the presence of the charge N matter, the U1 one-form symmetry is broken down to a Zn subgroup. The only operators which remain topological are the ones which furnish this Zn group. And this will bring us to our first connection between generalized global symmetries and quantum gravity through what's called the completeness hypothesis. This hypothesis, due to Polchinski, holds that in any gauge theory coupled to quantum gravity, there must exist states in every representation of the gauge group. It's often noted that this is related to the absence of global symmetries in quantum gravity, and from what we've seen so far, we can now see why this is. In U1 gauge theory, we saw that in the absence of any charged matter, we had this U1 electric one-form symmetry, which is broken to Zn when there are states of charge N. This means that if there are states of every charge satisfying the completeness hypothesis, then this electric one-form symmetry is broken completely. So here, there's a one-to-one correspondence between satisfying this completeness hypothesis and the absence of an electric one-form symmetry. This relationship has developed into a bit of standard lore, but this standard lore isn't actually correct in all cases. A counterexample is S3 gauge theory. Even though there's no charged matter in pure S3 gauge theory, there is still no one-form electric global symmetry. However, Even in this theory, there do exist more general topological codimension 2 operators. So recall that the hallmark of a one-form symmetry is the presence of topological codimension 2 operators which are labeled by elements of the group and fuse according to the group multiplication law. In the case of S3 gauge theory, we still have topological codimension 2 operators, but they're not labeled by elements of the group, they're labeled by conjugacy classes of the group. And they don't fuse according to the group multiplication law, but according to a slightly more complicated fusion algebra, in which 2 operators can fuse to a sum of additional operators. And relatedly, most of the operators do not have inverses. This is a hallmark of what, in recent literature, has been deemed a non-invertible symmetry. It's characterized by the presence of topological operators, but they obey this more complicated fusion algebra. And so the correct modification of the standard law in the case of S3 gauge theory is that completeness is equivalent to the absence of a non-invertible one-form symmetry. And this is an example of the more general statement. Completeness is equivalent to the absence of one-form invertible symmetries for a gauge group that is compact and connected or finite and abelian. But for a group like O2 or S3, the completeness hypothesis is equivalent to a non-invertible one-form symmetry. So in full generality, completeness is equivalent to the absence of a possibly non-invertible electric one-form symmetry. This is our first example of relationship between generalized global symmetries on one hand and these seemingly universal features of quantum gravity in the other. Although in this particular case, this relationship between completeness and the absence of symmetries is a statement that's true in quantum field theory as well. For our next connection between generalized global symmetries and quantum gravity, I need to introduce something called the weak gravity conjecture. This conjecture, due to these authors here, holds that in U1 gauge theory, coupled to gravity, there should exist at least one super-extremal particle. That is, a particle whose charge to mass ratio is greater than or equal to that of an extremal black hole, which in Planck units is just order 1. The weak gravity conjecture is also closely related to this phenomenon of symmetry breaking. So let's revisit this theory once again. We saw that in the presence of this charged matter, the U1 one-form symmetry is broken, as evidenced by the non-conservation of the Nether current. However, it's interesting to consider 2 limits of this theory. First, in the limit that G goes to 0, we find that D star F is once again equal to 0. And indeed, a more careful analysis reveals that the one-form symmetry is restored in this limit. Similarly, in the limit that M goes to infinity, we can integrate out the particle at low energies once again recover a one-form symmetry. This is interesting because these are precisely the limits which the weak gravity conjecture forbids. The weak gravity conjecture says that we can't have G goes to 0 at fixed M, or M over M Planck goes to infinity at fixed G. Now there's a way to make this heuristic argument more precise by studying the modification of the word identity. Recall that in the absence of the charged matter, we have this word identity. In the presence of the charged matter, the symmetry will be broken, and so this word identity will be modified slightly. If we insist that the modification of the word identity is order 1 at the Planck scale, so that there's no remnant of an approximate symmetry remaining at the Planck scale, the symmetry is badly broken by that energy scale, what we find is nothing other than the weak gravity conjecture bound. In fact, we find something slightly stronger. Not only does there exist a particle satisfying this bound, but in a sense, the average particle in the theory satisfies this bound. This points to stronger versions of the weak gravity conjecture, which I won't have time to discuss today, but have been extensively discussed in previous literature. The weak gravity conjecture is also connected to another generalized notion of global symmetries called higher group global symmetries. In a theory with multiple higher form symmetries, we may couple these symmetries, in general, to background gauge fields, and we can consider the background gauge transformations associated with these background gauge fields. In the most vanilla case, these background gauge transformations will take the simple form A goes to A plus d lambda. But in theories with multiple higher form gauge fields like this, we can have the situation where the gauge transformation of the kth background gauge field depends on the ith background gauge parameter. This term, this set of terms right here, is a hallmark of what's called a higher group global symmetry. And a prototypical example of this occurs in Axion electrodynamics. In Axion electrodynamics, we're coupling an ordinary gauge field A with field strength F to an axion, that is a periodic scalar field theta, through a Chern-Simons coupling of this form. This theory will have several electric and magnetic symmetries associated with A and theta. And here I've coupled the electric one-form symmetry that we're now familiar with for A to a background two-form gauge field, as well as the magnetic two-form symmetry for theta to a background three-form gauge field. The background two-form gauge field transforms in the vanilla fashion, but the background three-form gauge field has this modified transformation law. And this term right here is telling us that indeed we have a higher group symmetry. These modified gauge transformation laws lead to modified gauge invariant field strengths. F is equal to dA like usual, but G4 is equal to this modified set of terms. And this second term here is really the key one for our purposes. Because as noted by Brennan and Cordova, what this means is that if you turn on a background for the one-form symmetry, for A2, then this immediately leads to a background for the two-form magnetic symmetry. Which means that if the one-form symmetry is a valid symmetry of the theory, then the two-form symmetry must also be a valid symmetry. So the energy scale at which the one-form symmetry emerges must be no larger than the energy scale at which the two-form symmetry emerges. And we can further estimate these energy scales. Excuse me. We know from the first half of this talk that the electric one-form symmetry is broken by charged particles. If we're below the masses of all of the charged particles, we can integrate them out and recover an emergent symmetry, which means that the energy scale at which this symmetry is broken is at least as large as the mass of the lightest charged particle. Meanwhile, as argued once again by Brennan and Cordova, the two-form magnetic symmetry of theta is going to be broken at an energy scale which is no larger than the string scale of the axion string. That is, the string which is charged magnetically under theta, so that if you circle the core of the string, theta shifts by 2 pi. Putting these together, we find that the mass of the lightest charged particle has to be lower than the string scale of the axion string for consistency of the higher group structure. This, in turn, leads to interesting implications for the weak gravity conjecture. So the weak gravity conjecture can be applied not only to one-form gauge fields, as I've discussed so far, but also more generally to p-form gauge fields. Viewing the axion as a zero-form gauge field, the weak gravity conjecture gives us a bound on the instanton action. And if we view the dual of theta as a two-form gauge field, then the weak gravity conjecture gives us a bound on the tension of the axion string. If we further assume that the instanton action scales like 1 over g squared, which is familiar from QCD, or in the abelian case, follows from considering monopole loops, as argued by these authors, then putting this together, we find that the string scale of the axion string is bounded from above by g times m Planck. And if we combine this with the bound that we had on the previous slide for a consistency of the higher group symmetry, m less than m string, we ultimately find that the mass of the lightest charged particle is below g times m Planck. And this is nothing but the weak gravity conjecture for the gauge field A. So let's take stock of what just went down in the last couple minutes. We assumed the weak gravity conjecture for theta, as well as the magnetic weak gravity conjecture for theta. And then we saw that in the presence of this Chern-Simons coupling, which leads to a higher group symmetry, that we automatically found the weak gravity conjecture for A is satisfied. This is the phenomenon of weak gravity conjecture mixing. In the presence of Chern-Simons couplings, some versions of the weak gravity conjecture may imply others. And indeed, it's not an accident that just as how the electric one-form symmetry for A is mixed up with the magnetic two-form symmetry for theta into a higher group symmetry, so too do the weak gravity conjectures for theta imply the electric weak gravity conjecture for A? So up to this point, I've talked about how generalized global symmetries are related to these apparently universal features of quantum gravity theories. In the last few minutes, I want to focus not on quantum gravity in general, but on string theory in particular, and talk about how familiar phenomena in string theory can be understood as a consequence of the absence of global symmetries in quantum gravity. For this, I need to introduce one last class of generalized global symmetries. This is actually a particular class of higher form symmetries known as Chern-Weil symmetries. Chern-Weil symmetries are characterized by the property that their conserved Noether currents are given by wedge products, or in some cases, in the non-abelian cases, traces of wedge products of field strengths. Their conservation follows from Bianchi identities, and as usual, for global symmetries, we expect that in quantum gravity, they should be either gauged or broken. So an example where we see many of these Chern-Weil symmetries is in type 2a supergravity in 10 dimensions. This theory has a collection of higher form gauge fields, and considering wedge products of these gauge fields, we get a whole collection of Chern-Weil symmetries. For one example that we'll focus on today is the Chern-Weil symmetry with current G4 wedge H3, where here H3 is the NS-NS, the field strength for the NS-NS2 form, and G4 is the gauge invariant field strength for the RR3 form. Naively, this current is gauged by a coupling in the action of the form C3 wedge G4 wedge H3. However, it's actually broken in the presence of D4 branes, because the current is no longer closed. This naively seems like a contradiction, because we seem to be gauging and breaking the same symmetry. The resolution of this paradox is that there need to be additional world volume degrees of freedom on the world volume of the D4 brane. And indeed, one can argue that consistent gauging and breaking of these Chern-Weil symmetries, combined with gauge invariance, picks out the Chern-Simons action, which of course is the familiar action in string theory for the D4 brane world volume. This additional coupling to C3 means that the gauged current is now not going to be given simply by G4 wedge H3, which is indeed broken, but rather by this linear combination. This additional term is needed for consistent gauging and breaking of Chern-Weil symmetries. And more generally, throughout type 2a supergravity and 11-dimensional supergravity, the consistent gauging and breaking of Chern-Weil symmetries implies the existence of certain extended objects, namely branes for completeness of the theory, the existence of certain world volume degrees of freedom in order to have consistent gauging and breaking, as we just saw, as well as the ability for certain bulk degrees of freedom to dissolve in or end on others. For instance, one can argue consistent gauging and breaking of Chern-Weil symmetries implies that M2 branes can end on M5 branes in M theory. So the upshot is that much of what we know about string theory can be understood as a consequence of the absence of global symmetries applied to type 2 supergravity or 11-dimensional supergravity in the case of M theory. In conclusion, then, our understanding of quantum field theory has been revolutionized in recent years by generalized global symmetries. Meanwhile, there's been a great push to understand universal features of quantum gravity theories. In this talk, I've argued that these two areas are closely related. Much of what we know about quantum gravity in general and string theory in particular can be viewed as a consequence of the absence of generalized global symmetries in quantum gravity, which again means that generalized global symmetries hold power not only for quantum field theory, but also for quantum gravity. Thank you.
Okay, thanks very much. There's a question there, Dan.
Yeah, hi, Tom. I was just wondering, these Chern-Simons mixing terms are a crucial part of Axion monodromy. And I was wondering if there's any sense in which somehow, Axion monodromy seems to avoid all the usual weak gravity constraints, but somehow since you understand now the Chern-Simons term better, is it somehow constrained or still no?
That's a great question. I have thought about this from monodromy from a number of different lines, including the weak gravity conjecture. As far as I can tell, this is not giving us any new phenomenologically interesting constraints on Axion monodromy. So as far as I can tell, it's still sort of resisting all of these sorts of arguments. Yeah.
Hi, I wanted to ask about you said that the higher form symmetries have to be abelian, and I'm a bit puzzled by this, especially if you look at the higher symmetry, gauge symmetry groups. I don't see a reason why it should be abelian, if you can explain it.
Okay, yeah, so this is a good question. So why do higher form symmetries need to be abelian? So maybe kind of the cleanest, simplest way to understand this is in terms of these symmetry generators. So if in the case of an ordinary symmetry, these are going to be codimension 1 operators. And so if you imagine a situation where you have one of these operators at fixed time filling all of space, and you have another operator at a slightly later time, there's no way to push one past the other without the two of them intersecting, because they're codimension 1 in space-time. For a higher form symmetry, though, the codimension of these operators will be larger than 1. And so if you imagine two of these operators at different times, you can always rotate one around the other one, and in that way change the ordering of the operators. So because of this ability to deform one around the other, you can always change you can commute them, you can change the order, and you should still get the same result.
But if you look at the higher symmetry group, gauge symmetry, for example, supergravity, gauge supergravity, it's natural to have non-abelian higher form gauge symmetries. In the language is a bit like non-abelian gerbs, so I wonder why.
That's a good question. Well, these operators don't exist in such gauge symmetries, and so the argument that I just gave, I think, wouldn't apply to those. So I think that's the difference. But yeah, I guess I have to think about that further.
Questions? Let me ask the questions. Most of the higher group symmetries that you presented, and also I think the non-invertible, were continuous. So is there an interesting effect when you study the breaking of higher groups that are coming from discrete symmetries, like discrete one form and, say, parts of the zero form symmetry that's the center of the zero form symmetry? Yeah,
that's a good question. So first of all, one clarification that the higher group symmetry I showed, the electric one form symmetry in that is actually broken to a ZK subgroup. So we already actually did see one example where part of the higher group structure is
sort of continuous, and you just have sort of a U1 current for all of them.
That's right. So there still is that's right. So there still is a current there. So some of the papers that I discussed here, we discussed the generalization to the discrete case as well. The breaking of approximate symmetries at the Planck scale, for instance, can be understood as by looking at the modification of the word identity for a discrete symmetry as well as continuous. But as far as the higher group structure, the example that I showed here is really the one example that I've looked at in general. So my guess is there's probably a generalization and some interesting things to be learned from the discrete case as well, but that's on the to-do list.
Okay, let's thank Tom again.